What is this switch telling you actually? This tells you that the switch is being closed at t equal to 0. So that means the switch was open for t less than 0 for a long time. So which means that the circuit was at steady state at t less than 0 or at t equal to 0 minus. So at t equal to 0 minus, was there any current flowing when the switch was open is the question. Look at that everybody carefully. Was there a flow of current when the switch was opened? The switch was open at t equal to 0 minus and the circuit was at steady state. So when the switch was open, see here, when the switch was open, what do you think the current is? Is there a current flow? Is the question. Is there a current flow? If the current is flowing, suppose, which current, in general, I of t would flow. Okay. In particular, what is flowing? I of 0 minus is flowing. If I of 0 minus is flowing when the switch is open, what would happen to that I of 0 minus? It is 0 amps, which further implies that since the current through the inductor, see, there is inductor as well as the capacitor. This is not only the current passing through the capacitor, this is the current actually flowing through the inductor. And current flowing through the inductor does not change instantaneously. Okay, so it implies that I of 0 plus is equal to I of 0 minus, and that is equal to 0 amps. This is one thing that I have asked us to find out. See, this we have found out. I at t equal to 0 plus means it is I of 0 plus. Everybody understand that point? Now next what we need to do? Next we need to look at the circuit at t equal to 0 plus. To find out the first order differential and second order differential, we need to see the circuit at t equal to 0 plus. Okay, at t equal to 0 minus, the switch was open. At t equal to 0 plus, the switch was just closed. Okay, so I of 0 plus is 0. The current through the inductor is also 0. But now after some time passes by, okay, so let's see what is going to happen. At t equal to 0 plus, let's talk. At t equal to 0 plus, that is when the switch is just closed. Okay, how does the circuit look like? Everybody just copy down the circuit with the switch closed. The same circuit, but you'll be having the switch closed. Okay, so here is the switch. Let's say the switch is closed at t equal to 0 plus. Then you have R, L, and C. This is how the circuit looks like. Okay, so 10 ohms, 1 Henry, and 1 microfarad is the value. So 10 volts. Fine. Now, which current is flowing everywhere throughout the circuit? I of 0 plus is flowing, isn't it? I of 0 plus is flowing. Throughout the circuit, the same current is flowing. Now, apply KVL, everybody. Apply KVL. Just a sec. I'll be telling you the same thing that I told you yesterday because that makes a good learning. Everybody just observe when you are writing the voltage or current through inductor or capacitor is what we are looking at. Is everybody okay with that? Everybody just make this chart. Everybody just copy down. This chart would help you in many ways. Okay, voltage across the inductor is given by what? Voltage across the inductor. Is voltage across the inductor an integral equation or okay? Yeah. Voltage across the inductor is differential. Voltage across the capacitor is integral. Current through the inductor is integral. Okay, so let's write the current through the inductor. So it's 1 by L times integral of I. Sorry, we are writing current through, right? It's V dt. I of t is this current through the inductor. Similarly, voltage across the capacitor is this 1 by C times I dt. This is V dt. Okay, and these are differentials. So it is L di by dt, and this is C dV by dt. Keep this particular table with you. Okay, and seeing this, you can easily write the KVL and KCL, whichever is asked. Okay, so most of the times we are writing KVL. So let's go on with the KVL now. Everybody understand this, right? This is very important table. This will help you what? Get the things in correct way. Is everybody okay with this? I hope you have copied down that. Yeah. Yeah, fine. Now seeing this, we shall apply the KVL to this. Is everybody okay with that? Let's apply the KVL. KVL along the loop or the mesh. It's just one path. Okay. So KVL implies what? It's minus 10 plus 10 into I of 0 plus. Okay. Now, these are our voltage. KVL means we are writing the voltages. Voltage equations means we apply KVL. Okay. Current equations means we apply KCL. Understand that? So we are writing the voltage equations in terms of current. See here, I of 0 plus is current. Now, what is the voltage that is dropping across 1 Henry because of I of 0 plus flowing? Is that a differential equation or a integral equation? Voltage across the inductor. Voltage across the inductor. See, it is differential equation. So it's L into di by dt. What is L? L is 1 Henry. Okay. Di of 0 plus by dt. So this is how the voltage across the inductor looks like. Okay with that? Then plus. What is voltage across the capacitor? What is voltage across the capacitor given by. What is it? See here, it's 1 by 1 micro into integration I of 0 plus dt. Understand this? Okay. Now, what is I of 0 plus that is flowing through this? This is 0, right? So this is, so algebraic sum of all this should give you 0. Since I of 0 plus is 0, okay, this would be 0 and this would also be 0. Everybody understand? Since I of 0 plus is 0, okay, so this term as well as this integral term will go off. Fine. Now we are left with the first order differential. So what is first order differential? The first order differential is actually equal to 10. What would be the, therefore, di of 0 plus by dt is equal to what? Is equal to 10. What is the unit? Unit is amperes because current is there in numerator, and seconds because the time is in the denominator. This is how the things look. Fine. So take this as equation number 1. Okay. Now we have to take the differentiation again, because why do we need to take differentiation now? We need the first order differential and the second order differential. We've got the first order differential here. Okay, how to get the second order differential? So we have just marked them as zeros. So whichever terms are marked them as zeros, okay, so that is regarding equation number 1. So in equation number 1 they would be 0, but if we differentiate differentiating 1 to find what? D square I by dt square. What do we need to do? Okay, differentiate 1 with respect to t. Everybody differentiate. So if you differentiate this constant, that would become 0. If you differentiate 10 into I of 0, so 10 into di of 0 plus by dt plus d square I of 0 plus by dt square, okay, plus 1 by micro is there. When you differentiate, the integral will do go off and you'll be left with just I of 0 plus equal to 0. So this is substituting I of 0 plus equal to 0, right? So similarly here you would say substituting I of 0 plus equal to 0 implies what? I of 0 plus is 0 and di of 0 plus by dt equal to 10 amperes per second. So if you differentiate it, how it would look like? It's 10 into 10 plus d square I of 0 plus by dt square plus 1 by 1 micro, okay, into 0. This is how it is going to look like. So what does this mean? This means that our second order differential of the current at t equal to 0 plus is actually minus 100. Okay, I of 0 plus is there in the numerator, so it is ampere. T square is there in the denominator, so it is second square. So the second order differential is minus 100 amperes per second square. Is this okay with you, everybody? If you have anything to ask, you can ask me now. Let's go with another problem. Yeah, this is problem number 6, wherein we have a different type of a switch. Okay, so this switch will keep shifting from position 1 to position 2. Okay, and what is the symbol telling you? At t equal to 0, the switch position is changed from position 1 to position 2. Okay, and the problem statement said the circuit was at steady state with this switch in position 1. That means when the switch was in position 1, the switch was in position 1 for a long time. So when it was there in position 1 for a long time, the circuit was at steady state with switch in position 1. So that is the problem statement, and with that information you need to find out the current and first and second order differentials at t equal to 0 plus. Fine. So since we have to find out I at 0 plus, we need to see what is I at 0 minus. And to find out I at 0 minus, what do? We consider the steady state condition. Okay. So let's do that. First thing why we are doing it is to find I of 0 plus. At t equal to 0 minus, the switch is at position 1 and the circuit is at steady state. Everybody understand this point? So let's write the circuit now. Therefore, at t equal to 0 minus, therefore at t equal to 0 minus, what? C is open circuit and L is short circuit. Okay, hence the circuit becomes, in steady state we are writing this. Everybody write this: open circuit C and short circuit L with switch position in 1. Okay, how does it look like? Plus minus. Okay, this is 1. So this is the switch now. Switch is connected here. R is there. L is short circuited. Fine. Then you have this C, right? C is open circuit. And this is of no use. This particular branch is of no use. This is position 2. Okay, this much is of no use. So that means you can just neglect this. Fine. You need not have to. I'm just showing you since I have got the option to do that. This circuit is as good as this. What is the meaning? So if it is there or not, that it will not make any difference, is what you should understand. Okay, so just take down the values. This is 20 volts, this is 10 ohms. And what's flowing now? What is flowing throughout? I of 0 minus is flowing, mind you. Throughout I of 0 minus is flowing. Okay. So KVL implies what? KVL implies it's minus 20 plus 10 into I of 0 minus equal to 0. It further implies that I of 0 minus is what? 2 amperes. Okay. Now what statement you will make? We are doing this to find out I of 0 plus. What statement do we make here? You can make that statement, or you can just write. It's better you make that statement since current through since current through L does not change. You can ask me where is L there? Where is L there? You can ask me. This is current through the inductor. I'm saying that this inductor would act like a short circuit. It's not actually replaced, but it acts like a short circuit. That means the inductor is still there, but it's acting like a short circuit for the current flow. Is the meaning of that. That's why we call this current through the inductor. Okay, does not change instantaneously. Instantaneously. I of 0 plus is actually equal to I of 0 minus, and this is equal to 2 amperes. So we consider this circuit at steady state, okay, when we have to find out I of 0 plus or V of 0 plus. Remember that. So now what? We need to find out the first order differential and second order differential. Understand that? And for that, what do we need to see? We need to see the circuit at t equal to 0 plus. At t equal to 0 plus, where is the switch position? The switch position is at 2, because at t equal to 0, it is being shifted from 1 to 2. So at t equal to 0 plus, the switch would be at position 2. Everybody understand? Now take this. At to find a di by dt and d square I by dt square at t equal to 0 plus, isn't it? This is what we're doing now. Okay, so we need to have the circuit diagram at t equal to 0 plus. At t equal to 0 plus, the position of the switch is at 2. Okay, so that's, again, I'm not writing that. Yeah, plus minus, you have position 1, you have position 2 here with the capacitor connected there. Okay, now so this is how it would be looking for us. Okay, so this is 10 ohms, 1 Henry, and 1 microfarad. So this 20 volts is redundant. Okay, so this particular part will not be of any importance to me. Fine. So this is not coming into picture because this is open circuit. The current anyways will not flow through this. But earlier there was a current flow, right? Earlier there was a current flow at t equal to 0 plus. That current is flowing here through the inductor. What is flowing? I of 0 plus is flowing actually. Okay, see here, I of 0 plus is flowing here at t equal to 0 plus, and we have known what is I of 0 plus. 0 minus is when the switch was about to be closed. At 0 it is closed. At 0 plus it is just closed. When it is just closed, okay, the current would not change. Okay, so that's why with closed switch, okay, we still are with I of 0 plus. Understand that? So let's apply the KVL now. Okay. So when you're applying the KVL, again, you're looking at what? You're looking at voltage across the capacitor and voltage across the inductor. Okay. So again, you have to remember this particular table. Understand that? Okay. So this, if you keep for reference, the things will fall in place. You'll not have any problems doing that. Yeah. Can you apply that now? Can you apply the KVL? So the I of 0 plus from here, I of 0 plus from here will move into this. Okay. So this is dummy. This is not of any use to me. Okay. So you're just going through this part. So KVL implies what? What is the voltage across the capacitor? What is voltage across capacitor? What is it? 1 by C, okay, integral I of 0 plus, okay. Now we forgot to do something. Just a sec. I'll be explaining you that. Since the capacitor is open here, right? So we can find out another thing. We can find out another thing. Can you tell me what is V of 0 plus here? Is possible to be told here? V of 0 minus is there. What is V of 0 minus? Is 0, because this there is no current flow here, so we neglected that. Understand that? So current through the inductor does not change, so it is true. So if you have space, just you can make another statement that there. Sorry for that. Okay, what we are doing is we have found out I of 0 plus. We can similarly find out V of 0 minus. What statement do we make there? Since it is not asked, I understand. Since V across C does not change instantaneously, that is also, so V of 0 plus is actually equal to V of 0 minus, and that's equal to 0. Why it is 0? Everybody see here, this is V of 0 minus. Okay, what is the current flow here? No current flow, so this is supposed to be 0. There is no current flow here at all. Okay, the current is flowing through this is the dummy branch. Understand that? So V of 0 minus is actually 0. Okay, so this is another thing which was not asked, but in the next analysis it would be of help. So instead of dealing with this as integral equation, everybody, what we can do is this voltage is there, right? So we can consider this as voltage across the capacitor only. Okay, so let's first write the integral equation and then consider that as the voltage across the capacitor. So let's do that. 1 by C, okay, times I of 0 plus dt plus, what is that, 10 I of 0 plus, okay, plus L is 1 d I of 0 plus by dt is equal to 0. What is this? What is this? This actually is Vc of 0 plus, or you can just say, it is V of 0 plus. So this is V of 0 plus, okay, plus 10 I of 0 plus plus di of 0 plus by dt equal to 0. Now substituting what? Okay, substituting V of 0 plus equal to 0 and I of 0 plus equal to 2 amps implies that di of 0 plus by dt is actually equal to what? Minus 20. So this is 2, right? So this is 0. 20 comes to the right hand side and becomes minus 20 amp per second. This is how we find out the first order differential. Call this as equation number 1 only. Okay, so to find out d square I by dt square, what do you do to find out the second order differential? You need to what? Differentiate one with respect. When you differentiate this, what would be left behind? 1 by c times I of 0 plus would be left behind. So it is what? Differentiating equation 1 implies what? Just observe here. One we are differentiating. How does it look like? It looks like what? Everybody, can you try that yourselves? Start differentiating that. Yeah, you have 1 by c. Then integral would vanish and you will left with just I of 0 plus 10 times I of 0 plus is there. It would become 10 times di of 0 plus by dt. Then you have this, so which would become d square I of 0 plus by dt square. This is equal to 0. Okay, so further this implies what? This implies what is C given? C is given by 1 microfarad. So it is 1 by 1 micro is 10 power minus 6 into I of 0 plus. What is I of 0 plus? I of 0 plus is 2 amps plus 10. Okay, what is this first order differential? It is minus 20. Okay, d square I of 0 plus by dt square equal to 0. So what would this imply? This implies what? This implies that d square I of 0 plus by dt square is equal to minus 2 into 10 power 6 amperes per second square. You have to be a little careful regarding the uh, units there. If it is second order differential, the square would only be there in the denominator. Okay. If it is first order, it is no squares in denominator as well as the numerator because of the time and the current here. Understand that? Any problems you can ask me now. Just see what is this answer going to be. Okay, it is 200. Okay, on the right hand side minus 2 into 10 power 6. Okay, so these many amperes per second square.